Hello everyone, welcome to the video solution for physics. This is Edexcel IAL October 2018 Unit 3. So let's start. Question number 1. Which of the following is not an SI base unit? So you need to see the SI base and then unit. If you see Ampere is SI base unit, Kelvin is also SI base unit of temperature, second is SI base unit of time, while watt is a unit of power and this is not SI base, so your option is D. That means watt is not SI base unit, so your option is D. Question number 2. The diagram shows a vernier scale. Which of the following is the reading on the scale? For vernier caliper or for vernier scale reading, we have two types of a scale. The top one is called main scale, and we read the reading in millimeter, and you can see the millimeter written here. So the above numbers are in millimeter, and the lower ones are called vernier reading or vernier scale reading, and there is no unit for these. So the idea of taking measurement from the vernier reading is, or vernier caliper is, first of all you need to see the line before or close to the zero of the vernier. That means you need to see which line of main scale is close to zero of the vernier, and you can see that this is 15, 16, 17, 18 and 19. So here the main scale is giving you 19 millimeter, and then after that you need to look for which line of the vernier is best coinciding with the main scale. So if you see, this is the line number 1 here, it is not aligning. Line number 2 is still not aligning, 3, 4 and then 5 and then 6. If you see 6, line number 6 is best aligning with the main scale. So this is line number 6. That means in this scale this is 0.6. And how do you read the value? You add these two numbers. So 19 plus 0.6, that means 19.6 is your reading on that particular vernier caliper. So your option is C. Question number 3, 4 and 5 refer to an experiment to determine the viscosity of a liquid. A student dropped a sphere into a measuring cylinder containing the liquid. She measured the time taken for the sphere to fall through a given distance in liquid and repeated this several times. She recorded the time as 2.4, 2.5, 1.9 and 2.5. Which of the following is the best statement of time the sphere took to fall? So again, a typical question, you are given a data set and you need to find the estimated or the best value or the mean value, but be careful if there is any anomalous reading in the data set. That generally happens. So if you see 2.4, 2.5 and 1.9, so 1.9 is your anomalous reading and you need to discard that value. So you will have to find the mean value of only 2.4, 2.5 and 2.5. If you add these three numbers, that means if you do 2.4 plus 2.5 plus 2.5 divided by 3, because you have discarded 1.9. So you have just 3 data set value. And if you find the average, your average will give you the number which is 2.466, and if you see, the data set are given only in 2 significant figures, or you can say the 1 decimal place. So you round this off to 1 decimal place, and if you round it off, the answer will be 2.5. so your answer is D. Question number 4, which of the following quantities is required in the calculation of viscosity? And if you see the situation, because it's all about finding the viscosity. You are dropping a sphere in a liquid. So when a sphere falls through a liquid, and you know that during fall through a liquid, it is acted by three forces. The one is the weight, and the upthrust, and the drag force. And you know that for at terminal velocity, W is equal to U plus D, and W is mg, U is rho Vg, and D is 6 pi eta Rv. So if you see, what do we need to find the viscosity? We need radius of the sphere, velocity, and we need volume or size of the sphere, mass of the sphere, and rho. This rho is the density of the liquid. So we don't need mass, because in this equation we have mass here, but this mass is mass of the sphere, not mass of the liquid. So we don't need mass of the liquid, we don't need temperatures. What we need density of the liquid. So your option is A. Here is the density. Question number 5. Which of the following should the student not to do? Keep the temperature of the liquid constant, drop the sphere close to the side of the cylinder. Indeed, a student should not drop a sphere close to the side of the cylinder. It will affect the reading or the experiment. So a student should avoid to dropping a sphere close to the side of the cylinder. So option is B. Question number 6. A student determined the acceleration of free fall by dropping a cricket ball from an upstairs window. The student timed the fall using a stopwatch. Explain why dropping the ball from an upstairs window rather than from one closer to the ground improved the accuracy of the result. Clearly, if you have less height, like if you are dropping from here or you are dropping from here, so this is greater height. So if height is greater, so it will take more time, so time will be higher, so less percentage uncertainty. If you drop from lower height, so it will fall quickly, time to fall will be less, so greater percentage uncertainty. So it is advantage to drop ball from some height rather than closer to the ground. A second student stood outside and recorded the motion of the ball using the video camera and on a smartphone. Explain why this method would produce a more accurate result for the time than using the stopwatch. Clearly, a stopwatch include a reaction time, and if you are using video camera, so you don't have reaction time. This is one advantage. And of course, you are making a video, so you can replay, you can watch frame by frame, or you can rewatch to analyze the motion. Question number 7. A student is asked to determine the Young modulus of a metal in the form of wire. Using a graphical method, a standard laboratory apparatus is available. Write a plan for the experiment, and you should include all these points. So the point number A, draw and label a diagram for this experiment. This is all about Young modulus experiment, and if you recall, we do a typical experiment about the finding Young modulus of a wire, in which we use a table top like that, and then we use a ruler, and then we have some piece of a block here, in which we attached a wire passing over a pulley, So you can think like this, and then this is U clamp, and you can mark here like meter ruler, and then there is a marker here like that, and you can hang some weight. I'm sorry about that drawing. I'm not good at it, but that's how you can draw the diagram, and you can mention some of the name, like you can say this is your pulley, and this is your hanging weight or hanging mass, or you can say it is a load, and this is a meter ruler, this is a wire, and this is marker, U clamp, like that. So that's the diagram you need to draw for part A. Part B, list any additional apparatus required that is not shown in your diagram. Of course, this is young modulus experiment, so we need length and the area to find the stress. So we need, for area, we need diameter, and for diameter, we need micrometer screw gauge. So additional instrument is micrometer screw gauge we are going to need in this experiment. Part C, state the quantities to be measured. So we are going to measure length from the meter rule, extension from the meter rule, and diameter from the micrometer screw gauge, and load that we are going to hang on it. So original length, then diameter of the wire, and extension of the wire. Part D, state which is independent variable and which is the dependent variable. So if you recall that when you do your experiment, first you add some load due to which wire is extended. That means your load or your weight is your independent variable, and the extension is your dependent variable. So extension is dependent, and hanging mass or weight is independent variable. For one of the quantities listed in C, explain your choice of measuring instrument. So for C, we measure length and the diameter. So you can mention any one of the instrument. You can mention about the meter rule or the micrometer screw gauge. So we can say that we use micrometer screw gauge to measure the diameter because of the precision or the least count or the resolution of the micrometer screw gauge, which is 0.001, quite appropriate for measuring such type of measurement. F, comment on whether repeat reading are appropriate. So you have two choices to say about that experiment. You can say that yes, it is appropriate to repeat the reading, but measuring the extension by repeating the hanging mass, but you need to be careful that the mass stays within the elastic limit, then the repeated reading is appropriate. But if there is a chance of permanent deformation, then repeat reading is not appropriate. So it's up to you how do you write on and how do you justify. So that's how you can write one of the option, that repeat readings are appropriate in every step when you add the mass, but make sure that the load stays within the limit. Part G, explain how the data collected will be used. Include a sketch. Include the sketch of the expected graph. So you can explain how would you use the data. So remember, you have masses and you have extension that you are measuring. So first of all, you will need to find the diameter from the screw gauge, and using this diameter D in the formula for area, A is equal to pi D square by 4. And once you have an area, then you are going to find a stress applying, and stress is force per unit area, and this force is basically W, which is equal to mg. Once you have a stress, then you are going to find x strain, and strain is delta L over L or delta x over x. It doesn't matter, it's just extension delta L or delta x. So you can find the strain. Once you have a stress and a strain, then you can draw the graph of a stress against a strain, and then you have a straight line passing through origin. And once you have a straight line, then finding the gradient of this straight line, the gradient of this straight line will give you the Young modulus of the wire. So that's how you need to explain all these points for part G. H, explain the main source of uncertainty or systematic error. Main sources of uncertainty, you might have a parallax error in measuring extension because you are using meter rule and you are reading from your eye, so there might be a parallax error. Or systematic error, you can include zero error in micrometer screw gauge. Comment on safety, of course you must use there is a chance of breaking wire due to heavy load, so wire might snap and hit your eye, so you must wear goggle to protect your eye. Question number 8. In an experiment to determine the resistivity rho of a metal in the form of wire, the following results were recorded. Okay, criticize the results. Typical question again. You need to criticize the results. So you have a very few reading, only 1, 2, 3, 4, 5 sets of reading. You can say very few readings, and there is no repeat reading shown for current or the voltage. And of course, if you look at carefully like this and this, inconsistent significant figures are also used for resistance value. So that's how you can write the answer for criticizing the result. Complete the last row of the table. So if you see, complete the last row of the table, and the last row is this. And how do you do that? This is R and this is voltage and the current. So R is equal to voltage divided by respective current, which is 2.3. If you solve this, your answer is 0.869. 0.869, but again we need to give till 2SF is a better choice, so answer is 0.87, because everywhere we are using 2 decimal place, like, so 0.87 is your, so you can say that 0.87 ohm. Explain why a graph of R on a y-axis against L on the x-axis should be a straight line. You know that the formula that relates resistance and the length is resistance is equal to resistivity times of length upon area. And you know that if you rearrange this equation as R is equal to rho by A into L, and you can compare this y is equal to mx. So you can see that here m is the gradient, which is equal to rho by A. That's how this is the equation of a straight line passing through origin. So you need to say that this is the equation of a straight line R against L passing through origin with gradient rho by A, and as it is passing through origin, so your y-intercept is of course 0 because it is passing through origin. There is no C, like plus C. There is no C involved in this equation, so it is passing through origin. plot the graph on the grid provided and draw a line of best fit. So you will have to you need to plot graph against r against l, r on y-axis and length on the x-axis. So you need the value of length and the r. So this is the column that you can have in your previous part, and you can choose the axis. So length on the x-axis and r in ohm on the y-axis, and these are the scale 1, 2, 3 because length is starting from 1 to 3, and these are the resistance values. So if you when you plot the points, these are the points and this is the line of best fit. Part 2, the wire has a diameter of 0.27 millimeter. Use your graph to determine the resistivity of the metal. If you see the resistivity, so the formula for resistivity rho is R A by L, and if you see this formula R by L, this is the gradient M is equal to R by L. So if you find the gradient of that line, then you have R by L and multiply this gradient with the, so you can say resistivity will be gradient times the area. And for area, you can figure out the area using formula pi d square by 4, and the diameter is given in 0.27 in millimeter. Don't forget to convert into meter. So first let's find the gradient. So for gradient you will have to choose 2 points on the line other than those plotted ones. So we choose 2 points like these 2 black dot. I chose this, and the coordinate of these points are 3.1 and 0.92 and 1.25 and 0.37. And if you calculate the gradient, so gradient M would be equal to 0.92 minus 0.37 y2 minus y1 divided by x2 minus x1, 3.1 minus 1.25. And if you solve this, your gradient will be equal to M is equal to 0.297 ohm meter inverse, because this is R upon L. Or you can round this off till M is equal to 0.30. That's the gradient, and then you can figure out area. So area is pi d square by 4. Remember d is 0.27, so 0.27 divided by 1000, and you have in meter, and you put d here, you simplify this, and area would be 5.7 into 10 to the power minus 8 meter square, and therefore the resistivity rho would be equal to 0.30 times area 5.7 into 10 to the power minus 8. So resistivity is equal to 1.71 into 10 to the power minus 8 ohm meter. That's how you find the resistivity. Suggest 2 techniques which would ensure that accurate results are obtained. Technique, okay, because we are using micrometer screw gauge to find the diameter. So first technique is we must use repeated reading for diameter from different orientation, and we should use a mean value in order to avoid any random error. And the next reading is we must check the zero error in the voltmeter and the ampere meter as well as in micrometer screw gauge in order to avoid any kind of other errors. So that's how you can write the answer for that question. Thank you very much for this video. I hope you enjoyed it. Have a nice time. See you.